Hello students and welcome to my channel Maths Hub. So in my last video I was talking about a linear recurrence relation with constant coefficients and we solved for a homogeneous linear recurrence relation. So today I'll talk about a linear non-homogeneous recurrence relation and how to solve about it. Right? So let's see that how does a linear non-homogeneous recurrence relation look like. So we saw yesterday that when we have a recurrence relation equated equal to 0, that recurrence relation is known as a homogeneous recurrence relation. And when it is not equated to 0, that means this f of k is a non-zero term, then we call it as a non-homogeneous linear recurrence relation. I have already explained why is it linear, because the degree is 1 and it is having constant coefficients. So that is why it is called a non-homogeneous linear recurrence relation with constant coefficients. So what is the algorithm to solve this type of non-homogeneous recurrence relation? So the algorithm says that the solution contains two parts of it. The first part of the solution comprises of the homogeneous solution and the second part comprises of the particular solution. So in the last video, I've already talked about how to calculate the homogeneous solution. So just a little recap. What we will do, we will first convert the given non-homogeneous recurrence relation into a homogeneous recurrence relation by putting the right-hand side term equal to 0. So when you put the right-hand side term equal to 0, we will frame the characteristic equation from there and we will solve that characteristic equation to get the characteristic roots. And then depending upon the nature of the characteristic roots, we saw yesterday three solutions. When we have distinct roots, what is your solution? When we have equal roots, what is the solution? And when we have imaginary roots, what is the solution? And then we can get a combination of distinct and equal roots, a combination of equal and imaginary roots, so any combination you might get, but you need to know what are the standard solutions for those three types, right? So today we will learn how to obtain the particular solution. So for a non-homogeneous solution, the general solution will be the homogeneous solution plus the particular solution. So we have to calculate the homogeneous solution separately. We need to calculate the particular solution separately. We will add the two solutions and that will give us the general solution of a non-homogeneous recurrence relation, right? So now let us see that how do we solve the particular solution. So homogeneous solution I've already told you. So whatever is the homogeneous solution, we will denote it by SHK. So SK is the sequence that we are trying to find out and this H denotes the homogeneous solution, right? Now, how to obtain the particular solution? So in the particular solution, what we do, the method is that we assume a trial solution. We substitute that trial solution in the recurrence relation and we try to calculate the constants from there, right? So if your right hand side, that means if the function fk is the type of a constant, so it is c, then you will assume the trial solution to be b, another constant. We'll just replace the constant, right? The second case is when the right hand side function is a linear function, say c0 plus c1k, then we will assume the trial solution to be d0 plus d1k. So you will see that the type of the equation remains same, but we will only replace the constant c0 and c1 with some other constant d0 and d1. And by substituting it back in the recurrence relation, we can calculate the values of these constants, right? Similarly, if we have a quadratic equation, quadratic function on the right hand side, c0 plus c1k plus c2k square, then we will assume the particular solution to be d0 plus d1k plus d2k square, right? And likewise, if it is a polynomial of degree m, we will assume the particular solution also to be a polynomial of degree m. The only difference is all the constants will be removed and we will replace it with d0, d1, d2 and so on, right? Right. So this is what is the fourth case. Then we have the fifth case, that when the right hand side is an exponential function, so if it is of the type c into a to the power k, then we will assume the particular solution also similar. A to the power k will remain same. This constant c will be replaced by another constant, that is b, right? Now, so we have to keep these five cases in mind, and along with these five cases, one another important remark that you should keep in mind while making the trial solution is that none of the solution, the homogeneous solution, should match with the particular solution, right? So that means none of the terms of the particular solution should be present in your homogeneous solution. If it is there, then we will start multiplying the trial solution by the lowest powers of k, right? And we have to keep on multiplying with the lowest powers of k till any term whosoever was matching with the homogeneous and the particular solution, that matching problem is removed, right? So now, keeping these points in mind, let us try to calculate the solution for this recurrence relation, right? So we are given the recurrence relation as tk minus 7tk minus 1 plus 10tk minus 2 is equal to 6 plus 8k, where some initial conditions are given to us. So let us try to calculate first of all the homogeneous solution, right? So what is the homogeneous solution? So for the homogeneous solution, what we will do? We will put the recurrence relation equal to 0. So we have tk minus 7tk minus 1 plus 10tk minus 2 equal to 0. Then if you remember yesterday's method, we will replace tk by alpha raised to power k minus 7 alpha raised to power k minus 1 plus 10 alpha raised to power k minus 2 equal to 0. So you can take out alpha to the power k minus 2 common from all. So whatever is left in the brackets, I'm just writing that term. Alpha square minus 7 alpha plus 10 is equal to 0. So now this is my characteristic equation. So now let us try to solve this equation to get the characteristic roots. So what are my characteristic roots? Alpha square minus 5 alpha minus 2 alpha plus 10 is equal to 0. So we will have the roots as alpha into alpha minus 5 minus 2 into alpha minus 5 equal to 0. So the roots are alpha minus 5 and alpha minus 2 equal to 0. So we get two distinct roots, that is 2 comma 5, right? So if the roots are 2 comma 5, so what is my solution? We are interested in calculating tk. So now we are calculating the homogeneous solution. So we will write thk here. So it is c1 2 raised to power k plus c2 5 raised to power k, right? So this is my homogeneous solution. So now let us try to calculate the particular solution. So now what is the particular solution? So for the particular solution, we need to take care of the right hand side function. So what is given on the right hand side? The right hand side is 6 plus 8k. So you can see it is a linear function. So we will assume our trial solution tpk to be a plus b times k, where a and b are constants, and we need to calculate these values of a and b. So if it is a trial solution, we will substitute this trial solution in this recurrence relation. So the first one is tk. So tk will be a plus bk minus 7 times tk minus 1. So tk minus 1 will be a plus b times k minus 1. Then we have 10 times tk minus 2 will be a plus b times k minus 2, that is equal to 6 plus 8k, right? And before we proceed, we need to check the last remark, that none of the term in your trial solution should be matching with our homogeneous solution. So in the homogeneous solution, we have 2 to the power k, 5 to the power k. So there is no term such in the particular solution. So we can proceed further, right? So now let us calculate these coefficients. So let us solve this. A plus bk minus 7a minus 7bk plus 7b plus 10a plus 10bk minus 20b is equal to 6 plus 8k. So the constants are a minus 7a. So it is a minus 7a minus 3a. Minus 3a plus 10a is 7a, right? So a minus 7 is 6a, 6 and plus 10 is 4a. We'll get this. Now for coefficients of b, it is 7b minus 20b. So it is minus 13b. Now let us take the coefficients of k. bk minus 7bk is minus 6bk, right? Minus 6bk plus 10bk is 4bk. So we get 4b. This is equal to 6 plus 8b. Sorry, 6 plus 8k. It's not b. So it is 6 plus 8k. Now let us compare the coefficients on both sides. On comparing the coefficients of k on both sides, we get 4b is equal to 8. So this implies b comes out to be 2. And when you compare the coefficients of constant terms, 4a minus 13b is equal to 6. So we have 4a is 6 plus 13b. So it is 13 into 2. So it is 6 plus 26. That comes out to be 32. So this is 4 times a. So a comes out to be 8. So that means your trial solution or the particular solution will come out to be a is 8 plus bk. b is 2, so 2k. So this is my homogeneous solution. This is my trial solution, the particular solution. So what is the general solution? What is Tk? It is the sum of the homogeneous solution and the particular solution. So it is C1 2 raised to power k plus C2 5 raised to power k plus 8 plus 2k. Right? Now the question is still not over because we are given some initial conditions and we need to calculate the constant C1 and C2 from there. So let us apply the first initial condition T0 is equal to 1. So that means 1 is equal to, we'll put k as 0. So C1 2 raised to power 0 is C1 plus C2 5 raised to power k will become 1. So it is C2 plus 8 2k will again become 0. So the equation becomes C1 plus C2 is equal to minus 7. Right? Now let us apply the second initial condition. The second initial condition is T of 1 is equal to 2. So 2 is equal to C1 into 2 plus 5 into C2 plus 8 plus 2, right? So you can see 2 and 2 gets cancelled. So we have 2C1 plus 5C2 is equal to minus 8, right? So after solving these two equations, we need to calculate the values of C1 and C2. So after solving these two equations, we'll get C1 as minus 9 and C2 as 2, right? So put the values in the recurrence relation. So Tk comes out to be minus 9 into 2 raised to power k plus 2 into 5 raised to power k plus 8 plus 2, right? So this becomes your general solution. So you can see that we have calculated the homogeneous solution first, then the particular solution, and then what have we done? We have calculated the general solution. This was the general solution obtained. And if the initial conditions are given to us, using the initial conditions, we are calculating the constants. Right? Okay then. So now let's move on to the next question. So we need to solve sk minus 3 sk minus 1 minus 4 sk minus 2 is equal to 4 raised to power k. So let us see how to solve this equation. So let us first try to find the homogeneous solution. So what is the homogeneous solution? We will convert this equation into homogeneous type. So 3 sk minus 1 minus 4 sk minus 2 is equal to 0. So sk will be replaced by alpha k minus 3 alpha k minus 1 minus 4 alpha k minus 2 is equal to 0. So you can take out alpha k minus 2 common. So we will be left with alpha square minus 3 alpha minus 4 is equal to 0. Right? And when you solve this equation, we'll calculate the roots from solving this characteristic equation. So the roots come out to be 4 and minus 1. Right? Now if the roots are 4 and minus 1, both are distinct roots. So we get our homogeneous solution as C1 4 raised to power k plus C2 minus 1 raised to power k. Right? Now let us calculate the particular solution. So what is the particular solution? So for the particular solution, let us take the trial solution. So let SPK be equal to, it is 4 to the power k. So let us take it as a into 4 raised to power k, some constant times 4 raised to power k. Now let us check, is any term of the homogeneous solution same as the particular solution. So you can see there is a term 4 to the power k and there is a term 4 to the power k. So it is matching, right? So if any part of the homogeneous solution matches with the particular solution, we need to multiply with the lowest power of k. So the lowest power of k is k itself, k to the power 1. After multiplying by k, let us check whether they are matching or not. So now you can see that none of the terms of the homogeneous is matching with the particular solution. So we will assume ak into 4 raised to power k as our trial solution. So let us substitute this value back in the recurrence relation. So the first term is sk. So that will be a into k 4 raised to power k, then minus 3 into, what is sk minus 1? It is a into k minus 1, 4 to the power k minus 1. Then we have minus 4 sk minus 2. So it is a into k minus 2 into 4 to the power k minus 2 is equal to 4 to the power k. So you can see throughout the equation we have 4 to the power k. Only in these two terms 4 to the power k is missing. So we can split this power 4 to the power k into 4 to the power minus 1. So this can be rewritten as 3 by 4, and similarly this can be split as 4 to the power k into 4 to the power minus 2. So we can write this term as 4 to the power k by 16. So when we have 16, 4 and 16 will get cancelled and we will get here a by 4. So let us try to collect the powers of 4k. ak minus 3 by 4 ak plus 3 by 4a minus ak by 4 plus 2 into a by 4, so that is a by 2. So multiplied by 4 to the power k is equal to 4 to the power k, right? So from here you can see that these ak terms get cancelled. This gets cancelled. We are left with 3a by 4 plus a by 2, right? So that comes out to be 5a by 4, right? So 5a by 4 is the coefficient on the left side, and on the right hand side the coefficient is 1. So from here a comes out to be 4 by 5. So then what is my particular solution? SPK comes out to be, a comes out to be 4 by 5, k times 4 to the power. So you can collect these powers also. So the general solution, that is SK, will be C1 4 to the power k plus C2 minus 1 raised to power k plus, you can write this as k by 5 into 4 to the power k plus 1. Right? So I hope this question is understood. Okay. So now, as an exercise, you can try this question for practice and do write to me in the comment section that did you get the answer to this non-homogeneous linear recurrence relation. And we will be solving one more question. So sk minus 2, sk, so this is not t, but this is s here. plus sk minus 2 is equal to 1, where s0 is 2 and s1 is 5.5. So for the homogeneous solution, you can put this equation equal to 0. So we will have sk minus 2 sk minus 1 plus sk minus 2 equal to 0. So we will get alpha to the power k minus 2 times alpha to the power k minus 1 plus alpha to the power k minus 2 equal to 0. So on taking alpha to the power k minus 2 common, we will have alpha square minus 2 alpha plus 1 is equal to 0. So on solving the roots, we will get the roots as 1 comma 1. So what is my homogeneous solution then? SHK will be C1, 1 raised to power k, and these are equal roots. So if you remember, we will have C2 times k, 1 raised to power k. Right? Now, next is the particular solution. How to calculate the particular solution. So if you look at the right hand side function, it is a constant, that is 1. So what do we assume our particular solution to be? We assume the particular solution to be some constant. So let that constant be A. But when you check the constant A, you can see that it is matching with the first term. 1 to the power k is same as 1. So you can see that this term is getting matched with the term over here. So if it is matching, we'll multiply it with k. Now when you multiply it with k, what is happening? It is matching with the second term, because again 1 to the power k will become 1. So it is matching. So now we multiply it with another power of k, that is k square a. So now it is matching? No, it's not matching now. So we will assume this as our trial solution, right? So let us substitute it back in this equation. So the term is sk. So sk will become k square a minus 2 times sk minus 1 will become k minus 1 whole square into a plus sk minus 2 will become k minus 2 whole square into a is equal to 1. So let us take the coefficients of a. We have k square minus 2 times k square minus 2 plus 4k. Then we have from here k square plus 4 minus 4k equal to 1. So you can clearly see that k square will get cancelled. 4k gets cancelled. So we have 4 minus 2. 2a is equal to 1. So this implies a is equal to 1 by 2. So what is my particular solution then? SPK will become k square by 2. Right? So the general solution Sk comes out to be C1 1 raised to power k plus C2 k 1 raised to power k plus k square by 2. Now we need to calculate the constant C1 and C2 from these initial conditions. So the first initial condition is S0 is equal to 2. So S0 equal to 2 means 2 is equal to C1 plus C2k is 0. So this term becomes 0 again, k is 0. So we get C1 equal to 2. The next is S1 is equal to 5.5. So what is 5.5? Is it 11 by 2? Yes. So now 11 by 2 is equal to C1 plus C2 plus 1 by 2. So we get C1 plus C2 is equal to 1 by 2. You can take on the left side. It is 10 by 2. So that is 5. So if C1 is 2, that means C2 will come out to be 3. Right? So from here, finally, what is my solution then? It is 2 into 1 raised to power k plus 3 into k 1 raised to power k plus k square by 2. So this becomes your final solution, right? Okay. So I hope you have understood the video, right? The topic is understood now. So do practice some more questions and do let me know in the chat box whether you have been able to understand this topic or not. So thank you so much. So if you like the video, do hit the like button and do subscribe my channel. Those of you who haven't subscribed my channel, and believe in yourself and you will be able to achieve it. Thank you so much.